Hello everybody, welcome to this video on conformal mappings. Today we're gonna study the most famous conformal mappings, and these are gonna be really like the atoms you're gonna use to construct any conformal mapping of, let's say, quote unquote non-crazy domain. Okay, so whatever that means. So you can simply compose the maps that we're gonna see today to get a conformal mapping of that domain onto the unit disk or onto the upper half plane or the Riemann sphere. So this is something a bit more advanced, and it has to do with something called the uniformization theorem. But we don't need to worry about this today. We just need to discuss the famous conformal mappings and study their properties and how they map a domain to another. So just so that we're on the same page, let me remind you, or let's at least adopt this definition for this video. So we're gonna say that a domain D1 and a domain D2 are conformally equivalent if there exists a map F that goes from D1 to D2 that is biholomorphic. And by biholomorphic, I mean it's holomorphic, it's bijective, and it has a holomorphic inverse. Such domains are going to be called conformally equivalent. And now, usually, if we start with any simply connected domain, there are going to be some cases, but in the interesting cases, we can map that domain onto the unit disk conformally. And we ask this question: how can we construct that map? So if I give you a domain, I give you a simply connected domain, and I ask you, how do we map that to the unit disk, right? We're gonna try to answer this question in this video, at least for some of the domains that appear in research. This is particularly interesting to people in physics and in mathematics in general. So we're gonna go ahead and study that. But for us to be able to construct such mappings, we need to at least understand how we can map the unit disk onto itself, right? If we want to map some domain onto the unit disk, let us at least start by figuring out how to map the unit disk onto itself. Well, you can say use the identity map, sure, but are there any other ways of doing that? And the answer is yes. We can speak of the so-called automorphisms of the disk, of the unit disk, and by automorphism I mean a map that goes from the unit disk onto itself, and it's a biholomorphic map, or it's a conformal map in our language in this video. So I claim that every such map is of this form, is of this Blaschke factor form, and to get it, you just need to take A to be the pre-image of 0, and what you'd get is that f of z is going to be of that form up to a rotation. So it's going to be that thing up to a rotation. I'm not gonna go over proofs in this video, but I invite you to think of the proofs because they're not really that complicated. So if you think a little bit of this one, for example, why is it a holomorphic thingy? Well, A bar is gonna fall outside the unit disk, this makes the bottom have no zeros in the unit disk, and hence the whole thing is a holomorphic thing. And we're taking a ratio of polynomials of degree 1, and hence we're working with something bijective. And then we can speak of the inverse, and you can write down what the inverse is. by inverting some corresponding matrix. And I'll invite you to think about this. We're going to talk a little bit about how to invert such mappings in a few. But then you can see that the inverse is going to be also holomorphic easily. I'm interested in the question here that why is it that this map takes the unit disk onto the unit disk? You will see that in like studying conformal mappings, a very important thing to consider is where does the boundary go, right? So if you know where the boundary goes, so for example here, the boundary, if we walk on the boundary counterclockwise, we see that the domain is going to be to our left, right? And what's going to happen is if you map this domain like biholomorphically to another domain, the boundary is going to be mapped to the boundary. So you can take this as a theorem that we're claiming here. The boundary is going to be mapped to the boundary, and moreover, the orientation and the angles are going to be preserved. And what that means is that after I go to that boundary that I need to figure out, the domain I'm looking for is going to be just to the left of my boundary. And this reduces the question of knowing where a domain goes to the question of knowing where the boundary goes, which is much, much easier, right? So for example, here, if we, for example, ask the question, where does the boundary, which is the unit circle in this case, go under a map of this form? Well, we observe that if we take, for example, the modulus of that thingy, and we assume that z is of modulus 1, then here's what we have. So we have this thing is equal to the same thing as this thing, because that's of modulus 1. And the bottom, here's what I'm gonna do to it. So I'm gonna rewrite it first of all, and then I'm gonna multiply by the modulus of z bar, because the modulus of z bar is just 1, because the modulus of the z is 1. And then by the properties of modulus, this is simply z minus a over z bar minus a bar, because z bar is 1. And the modulus of the top is the same as the modulus of the bottom. So this is 1. And what happened is the unit circle got mapped onto the unit circle. And this is something that should tell you that, hey, the domain is going to be what's to the left to that unit circle, provided we preserve the orientation. And hence the unit disk here is going to be mapped to the unit disk by this type of mapping. Okay, so this is the first type of mapping you should keep in mind. And this is particularly useful in cases where, suppose you could find a map. Suppose I start with let's say with some domain, let's call it A, okay? And suppose I could find a map that takes that, let's call it G. Suppose I could find a map that takes that to the unit disk. However, in applications, we usually, for example, we usually like to have the property that, let's say g of 0 is 0, for example, or g at some point is 0, whatever that is. But I mean, if we construct a map, there's no guarantee that g of 0 is going to be 0. So what we can do in such cases is that we can introduce a new map, let's call it H, and what we can take is we can take A to be g of 0. And then we can introduce our new G map, our new conformal map, to be simply H composed with G. And the reason we want to do that is because G of 0 now is simply H of G of 0. But by our choice of A here, if I put G of 0 here, the answer here is going to be 0. So there are all sort of applications or all sort of useful things you can do with automorphisms of the disk. But it's interesting to know these for the sake of knowing them, I guess. Okay, so this is the first thing we want to discuss. The second thing we want to discuss is the so-called linear fractional transformations. And these are transformations. So what's going to happen is, if you're familiar a little bit with matrices, we are going to take a 2 by 2 matrix, A, B, C, D, that is of positive determinant, for example. And we're gonna take A, B, C, D to be real numbers, and then we're gonna look at a corresponding rational function. It's gonna be really the action of this matrix. If you don't know what action means, just think about it as it's this thingy. It's the action of this matrix on Z. And what's interesting about these types of maps is that they form the automorphisms of the upper half plane. And by the upper half plane, I mean all the complex numbers with positive imaginary parts. What's interesting about these maps is that they form the automorphisms of the upper half plane, but they have far more applications than this one. I'm gonna talk about these. Again, if we take the upper half plane and use one of these maps, let's call it, I don't know, let's call it F, then we're gonna also go to the upper half plane by holomorphically or conformally. And again, proving something like this boils down to proving where the boundary goes. And if we think of the boundary as, which is the real numbers here, the axes, the domain is just to our left, and we just figure out where the boundary goes. But of course, I'll let you think here how to find out where the positive numbers go and where the negative numbers go. But that shouldn't be too hard to see that they go to the real axes, and hence the domain is gonna be the upper half plane as well. Okay, so now we understand how two domains get mapped to themselves, but that's not really what we're interested in. We're interested in mapping a domain onto the unit disk, okay? And we're gonna go ahead and see that. So the first thing we're gonna see is, how do we map the upper half plane to the unit disk? Okay, so to map the upper half plane to the unit disk, we're gonna use something called a Cayley transform. And matter of fact, so here we chose the point I, which is here, and the point minus I, which is here. And we constructed this map by saying that it should be Z minus I over Z minus I. And of course, there's a proof why this goes to the unit disk, but you can also prove it by considering where the real axes go in this example. And as it turns out, as long as you pick a z naught here, and you pick the reflection of it, it turns out that what you can do is you can take any mapping of this form. Let's say z minus, let's write it this way, z minus z naught over z minus z naught bar. If you take a map like this, then you can map the upper half plane to the unit disk. So we choose I because it's just easier to work with. And this is a very famous map. It's called the Cayley Transform. Okay, so as I'm going here and giving you these tools, I invite you to take some time to appreciate and think and ponder over these, and probably at some point you just need to remember these, I guess, to be able to apply them to harder domains. But we're just seeing things, simple things. Okay, so far. All right. Now let's keep moving. Say I want to map a strip into the upper half plane. And the reason we want to map something into the upper half plane is because we're interested in the question in how can we map a domain to the unit disk, right? As long as it's simply connected and it's not of a special type. So how do we map a domain onto the unit disk? And to be able to do that, what we're gonna do is we're gonna map it to something that is easier to map to the unit disk, and then map that to the unit disk by composition. So since we know how to map the upper half plane onto the unit disk, we're gonna first map things to the upper half plane, and then hopefully map things back to the or forward to the unit disk by just composing. Okay, so another important map to remember is the exponential map. However, I want to warn you here that the exponential map is generally not injective because, for example, I don't know, if you choose a number z0 and you add 2 pi I to it, this is the same as e to the z0, and hence this map is not injective in general. However, if you restrict yourself to to imaginary parts, let's say if you restrict yourself to imaginary part of z between let's say 0 to pi, for example, just being wasteful here, so for example something like this, then this is injective. And particularly if I restrict myself to this strip with imaginary part of z being between 0 and pi, then we ask ourselves, what does the map e to the z do to it? So here's a simple way of seeing what's happening here. So I can simply, let's see, I can rewrite this as e to the x plus iy if I write z as x plus iy, and this is equal to e to the x times e to the iy. And what we know about the domain is that y is between pi and 0. And hence, what happened here is that I'm mapping this strip into a domain restricted with the output is gonna have an argument between 0 and pi, right? So the argument of the output is between 0 and pi in this case. And hence, what is that domain? Well, it's of course the upper half plane. The angles are between 0 and pi. But alternatively, you could have thought of this as you could simply have thought of this as a boundary problem, because this thing, which corresponds to y equals 0, maps, so by e of z, this thing maps to just e of x, so since y is 0, and as x runs over the real numbers, the output is going to be this positive thingy here. And then this thing, what does it map to? Well, it maps to, so this thing, it maps to e to the x times e to the iy, which is pi in this case, and this is minus e to the x. But e to the x is positive, and as x runs over the real numbers, we're gonna end up with this part of the domain. And since the orientation is preserved, the domain is going to be to our left, and hence this is the image. So you can think of it as in different ways. But another important, again, we're introducing some important maps. Another important map to remember, thus, is the exponential function. It maps strips to the upper half plane. And thus, if I wanted to map this strip onto the unit disk, I can use a Cayley transform that we spoke about here. I'm gonna use C for Cayley Transform to map that to the unit disk. And hence, to map this strip to the unit disk, we just need to compose C with e to the z. And this is an important observation. Okay, so let's keep moving and keep exploring more maps. So suppose we want to map something like a strip like this with an opening of an angle alpha to the unit disk. How would we do it? So let's see. So we need first of all to introduce the map z to the power pi over alpha, and here we're choosing the appropriate choice of branch cut for this map. Why does this map take this domain to the upper half plane? Let's see. So you can think about it again in two ways. So this map, it's like it's the map that takes input e to the I r e to the I theta, with theta being between 0 and alpha, right? And hence when I map it, it's gonna become r pi over alpha e to the I theta pi over alpha. But if I multiply by pi over alpha, this interval is gonna become, so if I call this now, I don't know, beta, then beta is gonna be between 0 and pi, right? So the idea is to get rid of the alpha and replace it by pi to be able to map to the domain that is squeezed between argument 0 and argument pi. So this is one way of thinking about it. The other way of thinking about it is to study what happens to the boundaries, and in this case we have these boundaries. So let me just mark them like that. So we have this boundary, for example. How would we map it? Well, if we just use this map and in this case alpha is positive, so I'm putting a positive number in place of z here, and guess what I'm gonna go? I'm gonna go to the positive numbers, like that. And for this thing, what's gonna happen is, over here, the angle is alpha, so we're working with points of the form r e to the I alpha, and hence when we raise to the power pi over alpha, which is our map, what we end up with is r pi to the over alpha times e to the I pi, and this is minus 1. So this is just minus r pi over alpha, and this is a positive number, and we're multiplying by minus, so we end up with this thing. And again, you can see that the domain is the upper half plane, the image. Okay, so this is another useful map. This is how we open strips, right? If we have this domain and we want to open it up, we can do that using a map of this form, depending on the angle we're working with. And again, as usual, we can map this to the unit disk via a Cayley transform, and the resultant map is going to be C composed with z pi over alpha. Okay, so I hope that you're keeping track of these maps we're talking about. All right, let's keep going, and we're gonna introduce now a map that is a very famous map. It's very famous in physics, particularly because sometimes we work with some PDEs and we like to solve them in a certain in some domain, and sometimes it's hard to solve them in one domain, but it's easier to solve them in another domain. And for example, when we speak of flow, for example, and we have some physics problem and we're speaking of flow, studying the flow in let's say in the exterior of the unit disk in the upper half plane, for example, could be harder than studying it here in this domain, for example, which is the upper half plane. So let me just correct this. So the upper half plane. What this map J of Z does is that it maps the exterior of the unit disk in the upper half plane to the upper half plane, which is a pretty important thing to do, as I mentioned, at least in physics. So how do we show that? How do we see that? Let's see. Here's how you can see it. So this map, here's what it does. Z plus 1 over Z. Let's see what it does. So if this is the unit disk, then this is 1 and this is minus 1. And let's see where 1 goes. So again, to be able to know where something goes or where a domain goes, you just need to know where the boundary goes. And this is what we're gonna do now. We're gonna just see where the boundary goes, and this will tell us where the domain goes. So we'd like to know where the boundary goes. And here's how we do it. Well, let's see. 1 goes to 1 plus 1 over 1, which is 2. So 1 goes to 2. And minus 1 goes to minus 1 plus 1 over minus 1, which is minus 2. And it's this point here. And now let's see where the positive numbers bigger than 1 go. Well, if you think a little bit about it, the positive numbers bigger than 1, so if Z is bigger than 1, i.e. Z is real and bigger than 1, then we will see that this thing is gonna go to the right of 2. In other words, this part here, it's gonna go to this part here. And then similarly, if Z is real and it's less than minus 1, then this thing, it's gonna go to the left of minus 2. In other words, what's gonna happen is this thing is gonna go here. And finally, if we look at this like this arc and we ask ourselves, where does it go? Well, it's also not hard to see. On that arc, the points here, they're points of the form e to the I theta, for theta between, in this case, if we're going in this direction, it's gonna be between minus pi and 0. And thus, let's see, so Z plus 1 over Z, so on the arc, Z plus 1 over Z is simply e to the I theta plus 1 over e to the I theta, which is, if you rewrite it, it's e to the I theta plus e to the minus I theta, which is simply 2 cosine theta. And cosine theta runs between minus 1 and 1 for theta between minus pi and 0, and hence this thing runs between minus 2 and 2. In other words, this thing here, this arc, it goes to this middle interval. And what this means is that the domain which is to the left of that boundary is going to map to the domain which is to the left of this boundary, which is the upper half plane. And hence this is the Joukowski map, and it's a pretty important map. And again, we could map this to the unit disk by using a Cayley transform. Okay, all right, that's it for today, and we're gonna do a follow-up video if necessary with like more conformal mappings. Thanks for watching.